Hi, this is Dr. Crisostomo, and this is Chapter 5, Discrete Probability Distributions. Now, this chapter, again, like Chapter 4, has a lot of equations, and I will definitely let you know what you do and do not need to be responsible for this course. So here are our objectives for this chapter. Basically, we'll be looking at probability distributions. These definitions should be quite familiar to you. So we have discrete and continuous variables. Discrete variables produce outcomes that come from a counting process, such as the number of classes you're taking, the number of students at WT, the number of mistakes in a given invoice. Continuous variables, on the other hand, are outcomes that come from a measurement. So height or weight, something that has a continuous amount of decimal points. So for these probability distributions, we'll just be looking at discrete variables. So that's Chapter 5. And then Chapter 6, we'll be looking at continuous variables. But for now, for Chapter 5, we'll be looking just at discrete variables. Again, discrete variables can only assume a countable number of values. So for example, if you roll a die twice, you can either get a 1, a 2, a 3, a 4, a 5, or a 6. And in this example, we can say, well, how many times does 4 occur if I were to roll the die twice? So it could appear 0, could appear 1 time, or it could appear 2 times in those 2 rolls. Here's another example. If you toss a coin 5 times, you can either get a heads or a tails. So for those 5 flips, you can get a heads either 1, 0, 1, 2, 3, 4, or 5 times. So we looked at the outcomes of those very simple events, and you can create a probability distribution for any discrete variable. And a probability distribution is a mutually exclusive listing of all possible numerical outcomes for that variable and probability of occurrence associated with each outcome. So for the die, we can either get a 1, 2, 3, 4, 5, or 6, and each of those probabilities would be 1 out of 6. Same with a coin. You can either get a heads or tails, and the probability of getting a heads or tails would be 0.5. So here in this chart, we have interruptions per day in the computer network, and we have 0, 1, 2, 3, 4, 5, and the probability that it would happen is here in the right column. Probability distributions are often represented graphically. So if we take a look here at this table, we can graph it with the number of interruptions down here in the x-axis and then the probability on the y-axis. And you get a probability distribution. I likely will not ask you to calculate an expected value, but I do want you to understand what it means and how it is derived. In the previous chapters, we have been able to calculate the mean, the variance, and the standard deviation. And similarly, we can also look at the variance and standard deviation of a discrete variable. So here are the formulas here. Again, I won't require you to calculate them, but I do want you to know that the idea of variance and standard deviation looks at the dispersion of those probabilities. So for discrete probability distributions, we'll be talking about 2 different ones that we can use. We can use a binomial distribution, or we can use a Poisson distribution. Again, we're just looking at discrete probability distributions in Chapter 5. Chapter 6, we will look at continuous probability distributions. And we use different probability distributions for different types of data. So for a binomial probability distribution, here are some characteristics of when you want to use that particular distribution. So when we have a fixed number of observations, so 15 tosses of a coin, 10 light bulbs taken from a warehouse, we want to use that binomial probability distribution. When each observation is categorized as whether or not the event of interest has occurred. So you get either a heads or tail of a coin, defective or not defective light bulb, it works or it does not work. That is a whether or not the event of interest has occurred. These observations should also be mutually exclusive and collectively exhaustive. So when the probability of an event of interest is represented as pi, then the probability of the event not occurring is 1 minus pi. And remember from the previous chapter, what mutually exclusive and collectively exhausted means. It means that if one occurs, the other cannot occur, and that the two of them together are going to cover the entire sample space. Another characteristic of that binomial probability is that there is a constant probability for the event of interest for each observation. So the probability of getting tail is the same each time we toss the coin. It's 0.5 the first time, 0.5 the second time, 0.5 the third time. It does not change. And then the last characteristic of a binomial probability distribution would be that observations are independent. So that means that the outcome of one observation does not affect the outcome of the other. For example, just because I got a tails on the first head does not increase the probability I'm going to get a tails on the next one. So they are completely independent. They do not affect one another. So here's some examples of the binomial distribution. Here we have a manufacturing plant labels items as either defective or acceptable. Again, there's that characteristic of whether or not the event occurred. A firm bidding for contracts will either get a contract or not. A marketing research firm receives a survey responses of yes, I will buy, or no, I will not. New job applicants either accept the offer or reject it. So when you're trying to determine if something should be using a binomial distribution, you do want to go back to these characteristics that we discussed. These next few slides I will go over quite quickly just because, again, they're a little heavy on the formulas, which I don't think are particularly useful in the real world. But you should still be aware that they exist. So suppose the event of interest is obtaining heads on a toss of a fair coin. You are to toss the coin 3 times. In how many ways can you get the 2 heads? So we could get a head, a tail, a head, a tail, a head, a tail, head, head. So there are 3 ways you can get 2 heads. And in this situation, it is very simple to calculate. However, in more complicated situations, we may need to use a combination equation. So here's a combination equation, and basically what it's calculating is the number of possible combinations that you could create for a given event. So here's another example. How many possible 3 scoop combinations could you create at an ice cream parlor if you have 31 flavors to select from and no flavor can be used more than once in the 3 scoops? Using this formula, we see that there are 4,495. Here's that binomial distribution formula. And what this formula tells us is the probability of getting a certain number of events of interest in a certain number of trials with a certain probability. So for example, if there is a probability of getting a tails, if there's a probability of 0.5 of getting tails on a coin flip, what is the probability that I will get 5 tails in 5 coin flips? So to calculate that, I would use this binomial distribution formula, where x is the number of interest in the sample, n is the sample size, and pi is the probability of that event. So again, I don't want you to know how to use this formula, but I do want you to understand what it is giving us. So what is the probability of 1 success in 5 observations if the probability of interest is 0.1? So say I've created a test to determine whether caffeine is in someone's system. and the probability that the test can correctly identify that caffeine is in the system is 0.1. So what's the probability of one success if I were to test 5 people? Well, using this calculation here, or this formula, I would get 0.32805. So the probability that I were to get one successful test if I were to test 5 people would be 0.32805. Here's another example. Suppose the probability of purchasing a defective computer is 0.02. What is the probability of purchasing 2 defective computers in a group of 10? So we're still using the binomial distribution formula. And if we were to plug that in, we would get 0.01531. And what this means is that the probability of purchasing 2 defective computers, if I were to purchase 10, would be 0.01531. Again, I don't need you to know how to use this equation or where to plug things in, but I do want you to know how to interpret this outcome here. Something to consider is that n and the probability for that event does determine the shape of your distribution. So here we have an n of 5 and a probability of 0.1, and here we have an n of 5 and a probability of 0.5.